Thank you for arranging this talk, and it's always very nice to visit the Newton Institute. So I'm from North Carolina State University in Raleigh, North Carolina, and currently uh, visiting Newton Institute for the SAIL program. So this work has been supported by uh, U.S. National Science Foundation. Also, I should mention the Army Research Office, my professorship fund, and also the fund that Newton Institute provides for making this visit possible through Hochschild Fellowship and the hospitality. So I'll start with okay. First, my collaborators. So both were my students. The first one is my former student Rei Zhu. So she started this work and then graduated. Right now, working with Google Alphabet. After this paper was submitted and we went through the revision stage, but then the reviewers asked for quite a bit of more stuff, and that's at that time because Ray was really busy with her work. So I recruited my current student Shubhrargo, and he finished the rest of the work and added quite a bit of new stuff, including multi-category classification. So right now it's pretty much finalized, and it's almost at the final stage of publication in Bayesian analysis. So I'll start with the motivation for this problem. What is meant by semi-supervised classification, in case you're not familiar with. So sometimes happens like in, so classification is like you get information about something and you want to put it one of the two or more categories. And in the training data, if you have all these labeling information available, that's the classical classification problem that we are all familiar with. And then you use the training data to train a procedure, and then when a new situation comes, you can put in the right category with high accuracy. But in semi-supervised learning, what happens is most of this at the training stage, most of these labels are not even available. So the measurements are available, but not the labels. There are only very few labels that are observed. One example is in the in financial transactions. So millions, billions of transactions happen, and then always there is some sort of algorithm that kind of monitors this. It's a very automatic that they try to alert in case of there's any issue or not. But if you really need to know whether that is a genuine transaction or a fraudulent transaction, somebody has to step in. It requires human verification, and that is a costly and time consuming process. So most of the time it's not done. So so that's why we get something but not quite labeled in the way we want. And there are other examples too. So this is a bit of repetition of what I already said. Classification in the supervised framework, data comes from two or more population, and each data unit comes with labels that mark the source, and then the classifier is trained using these labels. When a new observation comes, you apply it, and you measure how well you are doing. You can measure in several ways. The most basic one is the classification error, so whether you are right or wrong. So the proportion of wrong is the classification error. Of course, you have to when you train, you shouldn't use the same data for training as well as finding how well you are doing, because then that it will overfit. So, what you do is you in your training data you keep away a portion that is used to be used as test data for validation, and then you train this procedure, and then you check how well you did on the test data. And once you are satisfied, then you go for to implement this in new settings. The other part is training data, where it's used to train classifiers typically will have parameters, and you need to estimate those parameters using the first part of that data. And there are many classifiers in the literature. The discriminant analysis that Fisher introduced. So, this is basically an empirical Bayes classifier. If you knew everything, you apply the Bayes rule, but then there are parameters, you just estimate those parameters, and then it's empirical Bayes, and that's what discriminant analysis is. Logistic regression is also model based, but it in the regression setting it estimates the probability that something in belongs to a category given the predictor values through a regression line. And then there are other approaches like some more machine learning approaches like support vector machines, where they kind of propose a linear boundary and tries to find the best boundary that separates them using some loss function, the Hinge loss function. So, there are different types of classification rules. Semi-supervised learning is when we do not have all these labels. In fact, most labels are missing. So, how does one handle this situation of missing labels? In most traditional methods, including machine learning methods such as random forest. So, what they do is they throw away the unlabeled observations, just concentrate on the labeled ones, and then apply. Sometimes it still gives good results, but you lose valuable information from that discarding. So, so what our goal, or in general a semi-supervised learning's goal, is to also incorporate this partial information, that's the observations without labels, in the procedure, and the goal is to improve the classification performance. So, there are essentially two types of classification methods. One is known as the discriminative method. So, it's what it proposes is like a boundary, and then on this side is one, that side is other, and you try to find the best boundary, like support vector machines or kernel methods. So, those are typical such methods. And generative methods are that have to specify the distribution of the data up to certain unknown parameters. So, like discriminant analysis or logistic regression. We propose Bayesian. We take the second approach, the generative classification method, and we do it in the Bayesian way. So, and in such a way that we are able to handle a high rate of missing labels, something like 85–90% labels are missing. Now, Bayesian methods are particularly suited in this setting whenever there is some partial observations like this. So, anything that is not observed, you can put it in the same category as the parameters. So, there are two things, one is observable, another is unobservable. So, all you need is the conditional distribution of unobservable given the observable. So, when things are missing, you don't estimate plug in, because if you do that, you can do that, but then there is a sort of a possibility of underestimating uncertainty. Whereas, if you follow Bayesian method using a model, so then it's automatically incorporated in the setting. So, that's why. And secondly, these things can be generated one at a time using in a Gibbs sampling setting. So, computation is particularly friendly, and as we will see that each step is simple if you take one at a time. So, we will actually base our method on discriminant analysis. So, it is like discriminant analysis, we model this as like mixture of populations. So, some cases you have label, you know which source. If you do not have the label, you know that it comes from the mixture, and then you also do not know the proportions, mixing proportions, you do not know those parameters. But in it is completely a model description that can put it in the probabilistic framework. And the model is typically, so what kind of model you want to adopt? So, in classical discriminant analysis, with a linear discriminant analysis, the boundary is linear. In quadratic, it is when unknown covariances, you have quadratic decision boundaries. So, they are nice because I mean weird boundary shape is always confusing and kind of difficult to interpret, but with linear or quadratic, such simple curves as boundary is easier to understand. But in classical discriminant analysis, the assumption is based on its mixture of normals, and that is fairly strong assumption as in many situations. So, how do people address this in practice when you know that well normality is not really the situation? So, people use transformation. So, think that okay, log will probably make it normal, and then they apply log. So, this is done in a very ad hoc way, and a little more attempt to make it more automatic is something in the classical methods, well, something like Box-Cox transformation. So, that is a bit of very the Box-Cox transformation conceptually, it is still parametric because it tries to model the transformation through a parametric class, but it is notoriously unstable, the estimation. So, that can be a big problem. So, what we want to do is we do not rely on ad hoc choice of transformations or something like Box-Cox transformation, but let us assume that let us consider a semi-parametric model where there is some kind of transformation that will make it normal. That is the basic assumption, but you do not know the transformation. So, you incorporate the transformation also as a parameter in the model, and that is what will lead us to our method. So, this is the definition of this transformation model. It's so a random p vector x is called non-paranormal with parameters mu sigma. So, this is the mean vector, this is the covariance matrix, and transformation f1, f2, fp. So, these are coordinate wise transformation. The domain could be some interval in R, but in our case we standardize it to 0, 1, the unit interval. So, these functions are continuous functions, continuous and strictly increasing function applied to each component. So, different components, different functions are applied, so that the transformed random variable is a multivariate normal, and we write that as non-paranormal. And because we are not going to model this functions parametrically, that is why it is called non-parametric version of normal. So, this term non-paranormal was coined by Wasserman and his group. So, it is mathematically equivalent to Gaussian copulas, but the domain here is unit interval, whereas in Gaussian copula it is from real to real. So, okay, so one quick remark is that transforming something to normal is not a condition if you are looking at one single continuous variable, because everything you can transform to normal. So, the assumption is because you make it a joint normality, that is what the assumption. So, it is in some sense it is not really unreasonable to impose something if you already know that component wise things will be normal after transformation, then maybe with a little more push its joint normality is possible. So, that is what this, of course, it is an assumption, not everything will satisfy that. By the way, I want to make a quick remark here that there is another alternative to this, but we prefer this. So, one alternative was to, you can also do discriminant analysis without making parametric assumptions. So, for example, these populations densities, you just think that they are densities. So, it is a mixture, and then you can, based on whatever data you have, you can estimate those components. You have some label data, but there are two problems. First of all, so this is, for example, used in this notion of local FDR by Efron. They like estimate this null density, alternative density, and this local FDR is basically ratio of the estimated density. But density estimation ratio of densities is hard to estimate because it is bit unstable, and secondly you have very few data. So, non-parametric estimation of density is a bit too ambitious because you do not have much resources. So, semi-parametric is a very nice compromise because of several advantages. First of all, well, you do not have that kind of instability issue. With the transformation, you retain the structure of normality, in particular that kind of linear quadratic boundary. So, it is very nice, and this kind of so it is an additional parameter here, but it is much more nicely estimable. So, this is a very useful approach to follow. Yeah. Well, it is mathematically equivalent to that. So, here we are assuming that we have observations of p components. So, these are each component is taking value between 0 to 1 continuous, and then you can apply component wise transformation, not a joint transformation, component wise transformation to make it normal. So, in equivalent terms, copula would be something like, so you started with the real line, you transformed to the unit interval and then transform back to the real line. So, that would be the corresponding copula. So, but copula, we are not specifying the copula function, we are just modeling it. Well, sorry, the copula is actually the Gaussian, but we are not specifying the marginals. Well, okay. Now, this model needs some clarification because it is not quite identifiable. There is too much flexibility in it. So, in particular, as you can see that you can vary transformation and make all means possible or also all scale possible. So, you have to do something to either fix this mu sigma in some way or you can fix the transformations. So, fixing the location scale would be like putting mu equal to 0 and this joint covariance matrix, make it scale free, I mean scale it so that it is a correlation matrix, and then you can keep the transformations constraint free apart from the fact that they are smooth and monotone increasing. And the other approach is to keep mu and sigma free, but impose something on the transformation. So, for example, to fix the location of the transformation. So, at the middle of this interval, I can set the function value to be 0, and then the spread from. So, that is just chosen for nice symmetry, but it could have been something else, and fix it difference to be 1. So, in this way the location and scale of the function is fixed. Now, we follow the second approach for a couple of reasons. One is that first of all, we apply the same set of function to different populations. So, if we follow this, then we are kind of not, it is not quite clear what you will, how we will do, you probably have to shift these things. And secondly, it's harder to put a prior on the correlation matrix than a covariance matrix. Covariance matrix, for example, there is a conjugate prior, this inverse Wishart. So that's why we follow the second approach. So this is the constraint for on location and scale that will impose. And then we are supposed to put priors on this object and then develop some computing methods and then see how it works. So model is non-paranormal. So we have k populations. Each is p dimensional. So k can be 2, for the most cases it's 2, but in some cases it can be more. And the corresponding parameters are mu k, sigma k. And note that the transformation collection of transformations, that's the same for all populations. That has to be, that's the part of the non-paranormal assumption. Otherwise, it's not an assumption. And then we have to say something about how labels are missing, and we assume that it's missing at random. So that means it can depend on x, it can depend on the observed y, but not on unobserved label, right? So this semi-parametric model of non-paranormal and Marr assumption missingness allows us build a platform for Gibbs sampling through data augmentation. So the whole idea is to whatever missing you supply through the simulation step of MCMC, and then you have a sort of complete setting where your formulas are very, very well known. So these missing labels are generated within the sample, and the other thing is missing is the transformation. So both will generate, and once you do those two, then it becomes a classical discriminant analysis problem. So and there you can do discrimination using just simple Bayes rule. So that is the strategy. So it's conceptually very simple. Now question is, how do you put a prior on the function? So there are very well known techniques from non-parametric Bayes. The technique I particularly like is that of random series using B-splines. So you express the function as a linear combination of B-splines, and then you put prior on the coefficients. Now there are other possible bases also, but I particularly prefer B-spline because it has first of all, it has good approximation property, but that also is shared by something like wavelets or nearly shared by polynomials. But B-splines has another advantage when you are trying to restrict the shape. In order to make this increasing, what you need is just make the coefficients increasing. That makes it increasing. So it's a very effective way of putting a prior on functions that are automatically increasing, automatically ensuring that they are increasing. But so this means that this we put prior on theta so that they comply with the increasing restriction, but that is a little bit more complicated. So what we'll do is we'll start with something that is even more basic, namely these coefficients for each for each d. So for each coordinate, this collection of vectors multivariate normal. Now I know that it's not appropriate because they are supposed to be increasing. So I'll make that correction, but right to start with, you look at normal, and in fact there is not I don't have much prior information anyway, so there's no harm starting with something simple like some sigma squared times identity, and this mean vector is still unspecified, which I will specify in a way so that it's most beneficial. Okay, so now coming, the first thing is to address the constraint. So the functions are not arbitrary, they have to satisfy this constraint. At 1/2 it's 0, but look at this, this is this linear combination. So we constrain this to 0. Now, if we started with multivariate normal, this is a linear constraint, and similarly this is also a linear constraint. So, if you put a linear constraint on multivariate normal, it remains multivariate normal, okay, first. And secondly, observe some sort of sparsity. That is another property of B splines, that is, at any point only a very few of them are actually non-zero. So, the thetas that appear in the constraint are only those for which Bj 1/2 is non-zero, and in this constraint the Bj 3/4 minus Bj 1/4 is non-zero. That means either Bj 3/4 is non-zero or Bj 1/4 is non-zero. So, there are only a very few ones. So, in the conditioning, you are actually then conditioning on a very few coefficients. So, as a result, the formula for conditioning, so that is given by this matrix inversion. You are inverting very few low dimensional matrix. So, these are still linear constraints. So, what we can write it as the that as a constraint 1 multivariate normal, and then we see that these are two linear constraints. So, that effectively reduces the dimension of this coefficient vector by 2, and then by restricting and making it non-singular, we can just make it a lower dimensional, and then it is non-singular. Since from j is the number of B splines you used, it becomes a j minus 2 dimensional free normal, and then these means and variance covariance matrices are corrected according to the regression formula, which is very well known. So, we can write down, I am not writing it here, but it is very simple. So, this theta d bar is the reduced dimension coefficient, but that contains exactly the same information as the original theta d. And then finally, okay, so this is already I mentioned, and then finally one more thing to take care of. I know that thetas must be increasing, and that can be written down as a linear inequality constraint, and in the form of the reduced dimension theta d bar, it is still an affine constraint, which we can write down explicitly. So, this is a constraint. So, this is a nice region of the parameter space. So, the final prior would be this prior that we induce constraint to this region. So, it is a truncated normal. Now, it satisfies all requirements. It is truncated to this, and we know that if you start with conjugate prior, like the multivariate normal in this context is conjugate, because it is everything linear. So, its likelihood is Gaussian in the thetas. So, it is conjugate. So, if you take conjugate and you apply truncation to a region, it remains conjugate, at least technically it remains conjugate. So, that's that would be truncated normal, and it can be described in this way. So, the whole idea for sampling would be to how can we sample from this distribution, and there are plenty of nice techniques to do that. And finally, about the choice of the means. So, we could have started with, like, we do not really know them. So, can make them 0 0 0, but instead of doing that, we make them, these are supposed to be increasing. So, their prior means before the imposition of this restriction, if we make them all sort of increasing, then that boosts the chance of them being already ordered. So, that is what we do, and to boost them we just control this by two hyperparameters. So, it is one location, another scale, and then we follow the normal quantiles. So, that is just a choice that makes things a little bit easier. And if you did not do that, this will still work, but it will be in the beginning of the MCMC, there would be fewer samples that satisfy this restriction. So, generating from truncated distribution is easier when it already is in that region. So, that is why we do that. On mean and covariance, you could just put the improper uniform prior, but to be on the safe side, to not run on problems with singularity, we just make mu improper uniform, but on scale we are a little more cautious, make put a inverse Wishart with in such a way degree of freedom, so that you do not run into the singularity issue for any data. So, it is not very sensitive anyway. So, now I describe how to obtain posterior samples. So, first we have to initialize things. So, how do we initialize the transformation, the initialize the mean, initialize covariance, initialize the labels. So, this we have to describe. So, first start with the transformation. So, we have really no idea, we only know that it transforms 0 to normal. So, I mean uniform to normal. So, let us try something like normal CDF, but put a scale, so that it so if you take normal CDF, it automatically satisfies the first constraint. I mean not normal CDF, normal quantile function. So, then at 1/2 it is already 0. So, first constraint is satisfied, and we put this constant, so that the second constraint will be satisfied by if we choose this, right, the span is 1. And then that is the choice of the transformation function, but we have to translate it in terms of the coefficients, and we have to supply initial value of the coefficients. So, a very reasonable choice is choose the spline function that is closest in some useful sense, and this is the continuous L2. So, this way you can identify. So, that is the continuous least square problem. If you have to solve this, you will need to find this inner products of the spline functions. Most of them are 0, if they are sufficiently far apart they are 0, but some of them are non-zero, and then we will have to, and we tried to find in the literature, there is not exactly a analytic formula that is available to us. So, but we really do not need to care, because we replace the continuous integration by large scale Monte Carlo by drawing from uniform, and then it becomes a usual least square problem. You just use typical R packages to solve this. So, that is almost as good. Okay, so, that is how we initialize the data, and then latent observations. So, we have to get those latent observations, because those are supposed to follow normal. And how do you get the latent observation? Because you got the splines initial, and then we apply it on the observations XS. That is how we get the transformed observation wise. But in the so, this is the evaluation of the spline functions at those points, and then multiplied by these coefficients. So, this is how you get the latent observations. Initialize mu k and sigma k. Well, for mu k, what we do is we estimate this just based on the initial labeled observations, seems reasonable, and then initial labels are assigned in terms of proximity. So, an observation, if it has label, of course, you keep it. If it does not have, look at which mean vector is the closest, that is assigned its initial label. And now we have created all these labels. So, initialized everything. Now, we start sampling. So, starting with the transformation. So, we have to generate from this truncated normal. So, for that purpose, we used the Hamiltonian Monte Carlo method that really worked very well, is really suited for this kind of problem, for this truncated domain. So, it is those who are not familiar with that. It is basically a Metropolis Hastings move, but the proposal density is chosen by this Hamiltonian, and then you run it. So, that is one step in the Gibbs sampling loop. The other steps are generate mu, generate sigma, So, both are conjugate given the y observations, and these nks are counted labels with both assigned and generated labels. So, you update sigma, you update mu, and finally, the label updating. So, that is the Bayes rule. So, if it is not given, I mean, of course, if it is given, there is nothing to generate, it is observed, but unobserved labels. So, it is one of these k possibilities, and the corresponding probabilities are given by Bayes theorem. All of these are now available to us because we generated them, y, mu, sigma, the I mean, this contains the transformations, because once you generate the transformation, you have generated the y's, and initial value of this initial proportions also needed, but after that it would be conjugate, because you can put a Dirichlet prior and then it is conjugate. So, all these Gibbs steps can be done. There is still one thing we need to discuss, is like how many terms in the splines, how many terms of the spline basis you want to choose. And for that, instead of doing it within the Bayesian setting with, for instance, it can be done through marginal likelihood, but that is very, very computationally intensive. Or you can try some approximation like BIC, also kind of intensive. So, what we do is instead some took a clue from what other semi-supervised learning methods tried to do. So, one thing they tried to do is, and if there is a tuning parameter, they find it by from this heuristic understanding that when two populations meet and they kind of blur. So, that is where you have a low density, because in the center of the population you have higher density. So, as you move away from them and where it is one or more population, more than one population kind of are sort of similarly possible, that is where you should not have too many observations, because there the assumption is that the populations are kind of separated out. So, you look at the region where this is the ratio of classification probability between Lth and kth population. So, if it is between some 1 over m to m, where m is relatively small number like 3, then it is the moderate region where either way it is possible, and you for different values of j, you count how many observations fall here and choose a value of j for which this is small. That is the low density assumption, low density criterion. And by monitoring this for different j's, and this is a relatively simple way of tuning j, and it seems to work fine. So, that is what we did, and now I show you some numerical output. So far, unfortunately, there is no convergence theory. I would have liked to do something, but it seems this complicated problems with identifiability and these two things. One, it is just too much flexibility that we were not able to do that, but simulation shows that the method is doing really well. So, what we did is we compared with some of the possible methods. Most of them just use the label data, because they are not equipped to deal with unlabeled data. So, simulation setting is we have k classes and given dimension p, and then we simulate from these populations, and then we randomly well, I mean, instead of choosing values in our favor, we just choose values randomly. So, it is not trying to help any particular method, and then we also choose sigma case randomly. NL is the number of observed levels in each class, which set at low. And then we compare with methods like random forest, k nearest neighbor. So this is a ROC based classifier. Then there are others. I mean, we didn't compare in every situation. We didn't compare with everything because that's too many, or at least I'm not showing that, but we do these comparisons with different things, and also we run on some real data and see how they are doing. But I just want to mention that most of these methods are just based on only labeled observations. So, and judging criterion, one or more of this stuff like misclassification rate, that's the basic most basic one. You can more specialize to positive false positive rate, false negative rate, or some sort of synthetic number from this. So, this is called Matthews correlation coefficient. That so, if you are doing well, you should have more true positive than false positive, more true negative than false negative, and then this is a normalization, so that it keeps it between -1 and 1. So, high value close to 1 is desirable. For the other things, low values are desirable. Okay, so first starting with the simulated setting where non-paranormality actually holds, and the transformations are logistic. Of course, we do not know that, so we just run our method and then compare with random forest, k nearest neighbor, ROC based classifier. And here very clear, I mean the setup is like it's 10 dimensional, 15 dimensional, and this one is 30 dimensional, and this shows how many populations, and these are the total number of observations, labeled or unlabeled, and number of labeled is like this 5, 10, like this 5 each, here 10 each. Okay. So, it clearly has lower misclassification rate than all others, I mean by quite a bit of margin. The next one is when non-paranormality fails, and we want to see how robust our method is. So, fails in this following sense, that we have to apply different transformation for different populations, and here we consider only 2 populations. In the first, logistic is the right transformation, and the second, Gumbel is the right transformation, but we do not know that. So, we run our method pretending as if they need the same transformation, and here is the result. So, in this example, we monitored this quantity, false positive plus false negative divided by 2 times 100% out of, I mean false positive proportion. Okay, so this at the dimension, this is the it's a bit unbalanced, as you can see. So, we want to also test how it does to unbalanced data, and the number of labels pretty low, 3 or 5 in each class. So, comparing, so and by the way, here it is multiplied by 100 because the numbers were too low. For some reason, they are kind of separated, well separated. So, again our method is much better than all others, especially when you go down to, and that is interesting, when you increase dimension, it may look like increasing dimension makes the problem hard, but actually it is the opposite in this case, because higher dimension means you have more input, more information coming from different aspects. So, for example, when we look at, I mean in our mind we do calculations, we try to recognize people, when with some way we are actually doing a sort of very high dimensional classification problem, and we remember certain features, and then because so many features, it is almost perfectly identified who we are, or like other features we identify. So, that is what happens. So, it is no wonder, it is not a mistake that larger p we have smaller error. And then the rest would be a bit couple of real data applications. So, starting with the binary classifier, it's an ionosphere data. So, this data is publicly available from this website, and the goal is to classify. So, a radar detects some free electrons, and this could be good or bad according to. So, good means it shows some evidence of some structure in the ionosphere, and bad means it's some sort of noise, and you want to distinguish between those two. And this data has 34 continuous features, and actually it's a label data. I mean, all my examples are actually label data, but it's like 126 bad and 225 good cases, but we threw away most labels, 80–90% labels we throw away, 85% we throw away, and randomly, and then we run our method. So, in this example, so this one another method that so this is in terms of false positive, this is a little bit better, I mean somewhat better than, but in terms of false negative and MCC, which is the composite measure, we are doing better than everything else. Yeah, so that's the result from this one. Then the next example is pen-based recognition of handwritten digits. So again, this data came from this source. So it comprises of almost 11,000 instances. Each is so it's image data, and then you extract certain features. So you extract a 16-dimensional feature, and this data was collected from 44 writers. Each of them contributed 250 handwritten digital samples. So these are supposed to be numbers between 0 and 9, and then there are 10. So that means there are 10 classes, and you want to identify the written digit belongs to which category, 1 or 5 or 3 or whatever. So identify the digit. So here's the result. In terms of false positive, false negative, we are doing better than everything else. Random forest, k nearest neighbor, ROC based classifier. The next example is very similar, but in this time it's instead of letters, instead of digits, it's letters. So there's like 26 populations. So it's all uppercase English letters, 20,000 of them. So these character images were based on 20 different fonts. So you vary the font as well, and each letter is within these fonts. So randomly distorted to produce 20,000 unique stimuli, and finally, so that's some sort of noise was added, and finally each stimulus was converted to 16 features. So just like the previous example. So k is 26, and here are the accuracy levels: false positive, false negative. So again, letter recognition, our method is doing better than other methods in terms of both false positive and false negative rates. So next is I want to talk about quickly how to incorporate non-continuous variables in the setting. So far it has to be all continuous, because otherwise you cannot transform to normal. So we cannot quite transform this to normal, but what we can do is we sort of can do an auxiliary regression on this additional features and incorporate that in the mean. So that's how we modify the model as follows. If the label is k, is coming from the kth population, we add an effect to the of the additional predictor z, can be more than 1, in the mean, but the sigma is unaffected. So that's just like what happens in case of regression, and this coefficient we assume that this is same across different populations. Otherwise, we have too little information to estimate. In principle, it makes sense to make it dependent on the population, but if we are going to have very few labels, we are not going to make it to there. So that's why we make this assumption they're the same. And then once it's done, it's just one additional parameter psi, and you can just modify the MCMC procedure and can run this modified method. So here's one illustration. So this is data from, this is the last one actually. So it's a, I don't know much about these things, but it saw some sort of cancer type, and its data came from a hospital in Portugal, 165 patients, 23 predictors, continuous predictors, 26 qualitative ones, but based on, so because we had what the number of, because there's so few labeled observations, so we cannot handle all this because there would be singularity. So we just wanted to do an illustration. So we just chose one non-continuous variable, that was gender, and the labels are whether the person is dead or alive. Basically, you want to look at the measurement and kind of see how bad it is, so that person is most likely have died or possibly still alive. So then we run this method, and here is the result. So compared with I don't remember which. So this one has a little, has lower false positive rate, but in terms of false negative and MCC, the composite measure, our approach is doing better. And I believe in this context, false negative is a more important aspect than false positive, because kind of ignoring the signal may be more catastrophic. And in terms of composite measure also, it beats other methods. So overall, it's doing very well. If not, I mean, no method can do better than everything else in every situation. That's not possible, but it's doing really well through all these examples. So I think that's all. So I'll stop here. Thank you very much.
When you put the unseen labels, you have the example problem of cancer, not cancer. If you include these, don't you, like, asymptotically, you shouldn't gain any extra information, right?
But what you know is that when it's unlabeled, it comes from the mixture of these sources. So that's that's information. So it may not be directly used in lab, but it helps in estimating those parameters more accurately, transformation more accurately. Particularly, the transformation is the same for all populations. So it helps with other aspects. So if this were totally known, the populations were totally known, transformation was known, and only missing label, then of course there is no advantage. But it helps with the auxiliary things, and that's why it's doing better. Yes.
About the qualitative variables, I'm not sure to have understood everything, but if you have like 10 qualitative variables, you don't get a combinatorial problem to implement the model.
For non-continuous, we just regress it, and the transformation, then the observations are kind of correct. I mean, we make a mean correction. So we are not directly incorporating them in and all possible structure. We are not, there's nothing to actually trying to look at all possible configurations of this. It's just we observe them, this non-continuous, and then we put a correction to the mean to incorporate their effect. Right, right. And the example I showed, there's only one because we have to use a lot, much of the data to as test data. So that's why we have very few training data, and that's why we could not include many variables, because then we'll have more parameters than observed data. So that's the reason. But in principle, if you observe a lot, and in reality, you don't have to actually, when you implement, you don't have to do this, separate out this training data. I mean, once it's there, then you just run this method. So then you can incorporate more. Yeah, that's the assumption. Of course, I guess we can, but then it increases the number of parameters, and it's not necessarily more advantageous. I mean, it may be more flexible, but then you increase estimation error. So keeping things simple, and especially when it's regression, then regression affects only mean in the normal setting. So that's what we are sort of mimicking. So it's assumption. Of course, you can always do something different, but keeping it fewer, the number of parameters fewer, is also has its positive, its merits. So